When the average construction manager sees a cabinet with thousands of tiny wires, looks at a single line diagram, or sees cables laid out and running everywhere, their default response is to switch off. Everybody just assumes electrical engineering is too complex to even try to understand. Well, what if I told you there's really only a handful of basic concepts you need to understand? And that's exactly what we're going to spend the next hour or so trying to get our heads around. Obviously, I'm not promising that by the end of this video, you're going to have a perfect understanding of electrical engineering and be able to take job as a senior design engineer on the control systems for a nuclear power station. What I am saying is that to do your job as a construction manager, there's only a handful of concepts you need to understand, and learning them is going to make you better and more effective at coordinating and managing different trades, understanding the construction sequence, and ultimately delivering multidisciplinary construction projects. Every new building now has some sort of smart automation and building management system. All our old electrical infrastructure is getting replaced with renewable energy, and to feed the massive demand for artificial intelligence, we're building new data centers absolutely everywhere. Historically, services, mechanical, electrical, and plumbing scope, or MEP for short, typically make up around 20 to 30% project value and 30% of the scheduled duration. Now, I don't know for a fact, but I believe with the way projects are going in the future, this number is only going to significantly increase. On a data center, for example, around 70 to 75% of the construction costs consist of all these services, electrical, control system, refrigeration, HVAC, and they are now the vast majority of the project scope. And another shocking statistic I found is that electrical works, while only making up 30% of the project value, or less in a lot of situations, typically are on the critical path 70% of the time. So being able to more effectively manage these works will ensure that you spend less money and deliver your projects faster. Long story short, if you want to be a successful construction project manager, contracts administrator, estimator, or any other job working for major construction contracts, you need to have a good understanding of the fundamentals of electrical engineering and electrical construction. And that's my goal for this video. I'm going to talk you through the fundamentals of electrical engineering, power distribution, communication, and some other key concepts, the electrical design process, and the key drawings you'll need to be able to read and interpret, the construction process to take these drawings and put them into action, basics of electrical safety, and some common issues that I see on every single project I work on relating to the electrical scope of works. Again, this isn't going to be some deep dive into signaling processing or electrical transistors, because frankly, I studied electrical engineering and I don't even know or remember that stuff. It's really going to be about core principles and what construction industry professionals need to understand about fundamentals of electrical engineering, managing electrical works to achieve successful project time, cost, quality, and safety objectives. On top of that, all the slides I'll put in a link you can download in the video description. Let's get started with the fundamentals of electrical engineering. So electrical engineering can really be broken down into two sub-disciplines. We need to power stuff, so give stuff electricity so it can function and operate correctly. Things like electricity for a heater to generate heat, lights to operate correctly, or a pump that needs power to work, or we're trying to help things communicate with each other. So we're trying to build systems that transmit information between each other. For example, talking on the phone, using the internet, or a fire alarm sending a signal for danger to an alarm system. All these systems rely on communication systems. So those are the two core areas of focus of electrical engineering. But before we dive too much into that, I want to start with the basics of electricity. Maybe this isn't that useful for you to know on a construction site, but it helps round out and give you a comprehensive topic, and it doesn't take long to cover. First thing, let's understand what electricity actually is. So at the atomic level, as we know, everything's made up of different atoms. An atom is formed with protons and neutrons, and around these you have electrons. Electricity is these electrons moving through a substance which can transmit power. So electricity is the flow of these electrons through a conductor. Metals have free electrons that can jump between atoms, so that jumping between atoms is the flow of electricity. Electrons move relatively slowly, but the charge on these electrons transmits at the speed of light. So for an electron to move, it needs a force that push them, which we're going to talk about is voltage. It needs a complete path to flow through, which is a circuit. And if you have a break in that circuit, the electrons can't flow, so we can't transmit electricity. But before we dive too much into that, I want to start with the basics of electricity. Maybe this isn't that useful for you to know on a construction site, but it helps round out and give you a comprehensive topic, and it doesn't take long to cover. First thing, let's understand what electricity actually is. So at the atomic level, as we know, everything's made up of different atoms. An atom is formed with protons and neutrons, and around these you have electrons. Electricity is these electrons moving through a substance which can transmit power. So electricity is the flow of these electrons through a conductor. Metals have free electrons that can jump between atoms, so that jumping between atoms is the flow of electricity. Electrons move relatively slowly, but the charge on these electrons transmits at the speed of light. So for an electron to move, it needs a force to push them, which we're going to talk about as voltage. It needs a complete path to flow through, which is a circuit. And if you have a break in that circuit, the electrons can't flow, so we can't transmit electricity. All right, so that's electricity at an atomic level. Let's talk about electricity in practice. What are the core concepts you need to understand? The first one is voltage. So voltage is electrical pressure or potential difference. It's created by the separation of charges. So in a battery, this happens in a chemical reaction. In a generator, this happens when you have an electrical coil spinning through a magnet, which causes pressure on electrons. But voltage is measured in volts. And I love this diagram because it simply illustrates these concepts using the analogy of water. So we've got a good framework to think about it. So if we think about a water tank with an outlet through a pipe. So voltage is the height of the water in the tank. The higher the water is, the more pressure or the more force there is going to be pushing the water out of the tank. Current is the flow of electrons. It's a measure for how quickly electricity is flowing through a substance. Sorry, I shouldn't say how quickly, how many electrons are flowing through a substance. So it's measured in amps, and the direction convention is positive to negative, but the actual flow of electrons at the atomic level is negative to positive. AC electricity is when the current flows from positive to negative when doing this. And we'll touch on this more in a second because it's an important difference. And DC is when all the electrons drift in one direction. If we go back to our analogy of a tank above the ground, it's the amount of water that's flowing through the pipe is like the current. Resistance is the material that the electricity is flowing through is resistance to flow. So all materials resist electron flow to some degree. You can have conductors like metals, like copper and aluminium, which is what we make cables out of, which have a very low resistance, so electricity flows easily through them. Or you can have insulators like rubber, plastic, or air, where it's very difficult for electricity to flow through it. Resistance is measured in ohms. And going back to our analogy of the tank, you could think of the diameter of the pipe as a measure of resistance. If you have a huge open pipe, the water will flow out very easily. If you have a very small pipe, it'll be very challenging for it to flow through. So Ohm's law is the relationship between voltage, electrical pressure, current, the flow of electrons, and resistance. And Ohm's law states that voltage is proportional to both current and resistance. So if you have a very high current with a very high resistance, so you're getting a lot of electricity flowing through something that's difficult to flow through, it means you have a very high pressure. If you have a low pressure but a high current, then it would mean you have a low resistance. These are all basically Ohm's law just is the relationship between these concepts. That pressure is proportional to the rate of flow times the resistance. That makes sense when you think about it. If you can imagine something where there's a lot of water flowing through a very resistive thing, then must have a lot of pressure. So power is the rate of energy transfer. So power is proportional to the pressure and the rate of flow. So if you have a high pressure and a high rate of flow, it means you have a high power transfer. And power is measured in watts. Energy is the measure of power transferred over time. So power is an instantaneous, it's like speed. Energy transfer is like distance. It's like the measure of power transferred across time. And what do we care about in practice? Well, in practice, we have a source that provides some sort of power, like a solar panel, a battery, generator. We have a load. We have something that consumes electricity, like a motor that needs to spin, or a heater that generates heat. We have conductors, which is the path that electricity will flow most easily. So these are the copper, aluminium cables or bus bars. And then we need a return path to complete the circuit. So those are the fundamental building blocks of any electrical circuit, whether it's a power system or even a communication system. There's broadly two types of electricity we talk about, and they denote to whether the current constantly flows in one direction or it oscillates backwards and forward. AC is alternating current. It's where the voltage and the current oscillate between positive and negative at a frequency. So in the US, 60 hertz, in Australia it's 50 hertz. This creates this sine wave pattern of the voltage and current oscillating. The reason you get AC electricity is rotating machines like generators naturally produce this when they're spinning. Standard for all of our electrical grid infrastructure. So all our power systems operate at AC current. DC, on the other hand, is where you have electricity produced where the current flows constantly in one direction. There's no frequency component, and it's generated by things like batteries, which produce chemical reaction, or solar panels. It's required for all our electronics, so our phones, our computers, all operate using DC, and a lot of appliances also operate using DC. Increasingly, we're seeing large infrastructure, such as data centers or renewable energy, using DC systems because that's how they naturally operate. If we look at this in practice, you can see that DC, which is produced by something like a battery, is producing a constant flow of electrons in one direction, which generates this flat positive graph. Alternating current is produced by something like a magnetic coil spinning in a magnet, which causes the flow of electrons, but it causes them to oscillate forward and backward. While AC voltage is the standard for electricity grids, it wasn't always so. So what happened in the late 1800s when we had the first power stations is they actually ended up being direct current power stations. First power station in Pearl Street, New York City, 1882, was a DC power station, which worked fantastically for local distribution. The core challenge of this, though, is it was difficult to transmit power over long distances. The reason this is because if you go back to our formula for power, so our appliances use power at like 200 volts, 240 volts, depending where you are. When you need to transmit a huge amount of power, the power you're transmitting will be proportional to the voltage times the current. So if you have a low voltage, it means you need a high current to transmit a lot of power. But if looking at this formula, if we replace voltage with I squared by R, we can see that the power losses in the transmission line will be proportional to the current squared times the resistance, which means you're transmitting power at a very high current. Then even if the lines have a small resistance, you'll lose a huge amount of power in the transmission lines, basically making it not very efficient or effective at all. So to efficiently transmit power across distances, you need to step up the voltage. So instead of transmitting it at 200 volts, you need to transmit it at 20,000 volts, 60,000 volts, depending how far you're transmitting it. The problem with DC electricity is back when these systems were getting designed, back in the late 1800s, there was no easy way to step up DC voltage. Now we can do it with rectifiers and power electronics, but they are relatively recent advancements. Back when these systems were getting designed, people were exploring how to use them. There was no good way to step up DC voltage, but there was a very easy way to do it with AC voltage, which came from power transformers. So because power transformers could easily increase voltage, meant we could transmit electricity over long distances, meant that we eventually adopted an AC electricity grid. Now, we've established the difference between AC and DC. Within AC, so alternating current circuits, there's two core types. You can have a single-phase system or a three-phase system. A single-phase system is a two-wire system. You have a positive and a neutral, and you have a single sine wave. The voltage of the system is measured between the positive and the neutral. That's what you see when you see a typical AC sine wave graph. This is what's used in residential homes, small offices, lighting circuits, and basically low power applications. The thing is though, that generators don't typically have one positive and one negative, they have three. So naturally, these generators produce three different sine waves operating together, which is referred to as a three-wire system. The thing with a three-wire system is you're actually transmitting 3 times as much power with only one additional wire. So a three-phase system has 3 wires, but you're transmitting 3 times as much power. And the reason that's possible is because the 3 sine waves actually cancel each other out, so you don't need a return neutral path. So generators produce this natural 3-phase power. It's used in large power applications, industrial equipment, elevators, large HVAC units, data centers, and basically you get 73% more power for the same equivalent wire size. You get constant power delivery without pulsation. It's more efficient for motors, and you basically can transmit more power for the same amount of conductor sizes. Now, there's 2 different ways to wire a 3-phase system. You can have a star system, which has a neutral, which is better for unbalanced loads because it's got this return path, or you can have a delta system. Both handle the same 3-phase power, they're just used for slightly different applications. So that's basically AC and DC electricity, single phase and 3-phase systems. Now let's talk about an incredibly important concept for electrical safety, which is earthing. You've probably seen the green and yellow wires everywhere, maybe not properly understood what they are, but in practice, all electrical systems need earthing for them to be able to operate safely. Why is this? Well, if we look at an example of, say, you're in your house, you're operating an electric oven and it has a live wire and a neutral. For whatever reason, it was badly installed and the live wire disconnects and touches the frame. If you walk along now and touch your oven, you will suddenly connect the circuit from the electrical equipment to the ground, and the fault current will pass through your body, which is incredibly dangerous and will give you an electric shock or may even electrocute you if the fault current is big enough. Now, what does earthing do? So earthing ensures that if there's any fault on the system, all of the metallic components of the system are bonded to ground. So because there's this earth here, now when the live wire touches the frame of the equipment, the fault current will pass through to ground, which ensures that if you touch it, you might get some sort of shock, but you won't get nearly the same amount of shock as the lowest resistance path to ground is through the earth connected to the equipment. This will also ensure that the circuit breaker that's protecting the system will trip because the fault current will be significant enough to trip the breaker. Without it, in this situation, if you've got an overcurrent protection on the circuit, because there's actually no path to ground until someone touches the device, the circuit breaker won't trip. So basically, that's why all these green and yellow cables run everywhere on power systems. It's ensuring that they're safe to operate and safe to touch, that overcurrent protection works correctly, and if you get lightning strikes, it actually limits the voltage rise. So earthing, an incredibly important concept. We're going to talk about it a little bit more later so you properly understand the relevance and importance of it. Now, to round out the fundamentals, I want to talk a little bit about some other important concepts. So the first one I want to talk about is that the idea of apparent or reactive power. So what can happen in power systems, and I'll talk about why this happens in a second, is that you have a waveform for the voltage of the system and you have a waveform for the current of the system. Depending on the type of load connected to the circuit, you can actually get voltage and current to get out of alignment, which means when the voltage is positive, the current's negative, or vice versa. What happens in this situation, that instead of producing active power, which is voltage times current, you get reactive power. So reactive power, again, it's when the voltage and the current are out of phase with each other. This reactive power, if you think of it like a beer, the actual beer is the active power, the froth on top is the reactive power. So using up the capacity of the system, it's using up the contents of the glass, but it's not actually doing anything useful. So we want to try and minimize the reactive power component of a system by ensuring current and voltage are always in sequence. Power factor is a measure of the ratio of the active power to the apparent power. So a power factor of 1 means that the voltage and current are perfectly in sync. A ratio of less than 1 means that there's some out of sync between the two, and the active power being transmitted is less than the apparent power. Any AC system won't have a power factor of exactly 1. It'll be some number between 0 and 1. So low power factor means that we've still got to size the system, the size of the cables, the size of the generators is all based on the apparent power, but we're only transmitting useful active power. So low power factor is bad. We want a number as close to 1 as possible because it reduces waste in the system. The reason you don't always have a power factor of 1 is because of inductance and capacitance in circuits. So inductance are things like coils, which basically make it difficult for current to flow through, but easy for voltage to flow through. So if you think about it very, very simplistically, I'm sure this isn't actually what happens in the actual physics, but you can think about it, the voltage passes through slightly faster than the current, which causes the voltage to lead the current, which causes this gap between the two and generates the apparent power. Capacitance is the opposite. So capacitance is where the current travels through faster than the voltage. So you get the current leading the voltage, which causes the opposite effect. So ideally what happens is things like motors, transmission lines generate inductance. Then we need to compensate for this by installing capacitor banks within our system, which you see a lot on renewable energy plants. A lot of renewable energy plants to connect to the grid are actually mandated to install capacitance because power electronics are things, the inverters that use the DC rectifiers, they cause a lot of inductance. So to compensate for this, they're often required to install capacitor banks. And the final concept of power quality issues is voltage drop, which I've already spoken about a little bit when I was talking about why we chose to adopt an AC system versus a DC system. So voltage drop is where you have some resistance in the conductor or the transmission media. You have a current flowing through it. So if you start with 240 volts, you have current flowing through it, and then you have a resistance in the line. At the actual source where you're going to consume it, or the load, I should say, you might have 230 volts or 220 volts, depending on the losses in the line. So the way we mitigate this is larger cable sizes have less resistance, so you have lower voltage drop. Okay, the final concept I want to talk about are the different types of loads that we deal with. So we've already spoken about what inductive and capacitive is and the impact of that on the overall power system and the quality of the power. So we can have different types of loads. We can have purely resistive loads. So these are things like heaters or incandescent lights, which have a power factor of 1, which are very straightforward calculations. You can have an inductive load. So these are things like motors or transformers that have a lot of coils like this in them. They'll cause the voltage to lead the current and have a power factor of less than 1. They require reactive power to produce them. So again, producing more of the reactive power that isn't actually necessary for the proper functioning of the loads. And we can also have capacitive loads. So capacitive loads are very rare in terms of primary loads, but they're often installed, such as capacitor banks, to help with power factor correction. We can also have non-linear loads, which are electrical, which use rectifiers, things like LEDs or drivers, which draw current in pulses and again can cause harmonics in the system. Final thing is that, and this is very intuitive, but not all loads are going to be used 100% of the time. So demand factor is an adjustment of the load based on how often it's going to be used. For example, your lighting in your house, you might only use it during the day, but it's not going to be used at night. So that might have a demand factor of something like 50%, or your toaster, you might only use for 2 minutes a day. So if you're sizing a system, you wouldn't size it assuming the toaster is always on because you're going to drastically oversize the system. So demand factors are standard applications we apply to different types of loads to adjust them for how much they're likely going to be used. Okay, now we understand the fundamental theoretical basics. Let's now move on to talking about power distribution systems. how does power go from a generator to an outlet? We're going to build on our fundamental theoretical foundations. We're going to talk about in practice what the equipment is, the structure, the technical architecture, and how power systems actually work. At the end of the day, if you're a construction manager, these are the systems you're actually going to be building. Or you might not be working on a power station, you're going to be working buildings, commercial facilities, hospitals that use all of these different bits of equipment. So I'm going to start with the power network, which I'm going to do a super brief overview because this would only be relevant if you're working on actual generating stations or transmission lines. Then we're going to spend a lot more time talking about how loads are connected up and how power goes from an incoming source that is spread through a facility and connected to the end appliance. Okay, so the power network. How do power networks work? Well, power is generated at generators. So we might have a coal power station, we could have a nuclear power station, we could have gas engines, we could have renewable energy facilities. These are sources which generally are then produce power at something like 10 to 25 kilovolts, depending on the specific source, and then we'll connect to a step-up transformer. So a step-up transformer will take this 10,000 volts or 25,000 volts, whatever the generator is producing, and step it up to transmission lines. So transmission lines operate at higher voltages. Again, we spoke about in the last section that this is essential because it ensures we have minimal power losses when transmitting power long distances. Our solar farm might be 5 hours away from a city, so we need a way of moving that power efficiently without losing too much of it to where the power is actually being used. So that's done through transmission lines, which could step up the voltage to 500,000 volts, 200,000 volts, 138,000 volts. And then this brings this into the point where all our loads are. We then have a step down transformer. So we take the 500,000 volt input from the transmission lines, step it down to something like 11,000 volts. And this is how it's distributed through a system. So connected to the distribution network are our customers. So you could have large industrial customers, like for example, a data center might connect directly to the distribution network at 26,000 volts, 11,000 volts or whatever. You could then have customers that connect on the low voltage side where there's already a distribution transformer that steps it down to 240 volts. For example, your house would connect at the low voltage side. You don't have a transformer in your house that steps down the voltage. That comes directly from the street supply. Consumers can either get single phase or three phase connections. All residential homes, small offices, buildings, things like that will have single phase supplies. Large consumers, most buildings or industrial facilities will have a three phase supply. So that's a super quick overview of how we go from a generating station through transmission lines to a step down transformer to the customer connections. Let's now dive a lot deeper into electrical loads. Unless, as I said in the start, unless you're working on power stations or transmission lines, most of your dealings with electrical engineering is going to be through load distribution. How do we take the power from the street and deliver it to the appliance that's going to be using it? This starts with the incoming supply. This is where we connect the electricity distribution network. We're working on a large piece of infrastructure like a tunnel, a data center, a hospital. We'll generally connect on the high voltage side and have our own internal transformer. But if we're working on a commercial building, residential, these sorts of things, we will have a low voltage connection. This connection can be an overhead service like most houses where you have a wire coming directly off the residential transmission lines, or it can be an underground service where you have conduits running into your facility. There would then generally be a single piece of equipment which has the service entrance equipment. So this might be on a building, the main switchboard, or on a residential or small load, this will be your house's distribution board. This piece of equipment will be the termination point for the utility connection. It will also probably have some sort of fuse or circuit breaker, and it will also have your metering equipment. So this is where you measure how much power you're being produced, and there might also be surge protection. So if we look at this is a larger facility. This is some sort of industrial facility. You can see the incoming cables are these larger cables here, when the outgoing cables that spread the load through the facility are here. Within this board, there'll be some metering and a circuit breaker that protects the incoming cable. So On a large facility, this is the main switchboard. On your house, you wouldn't really call it a main switchboard, but you might just call it a distribution board. Basically, the main switchboard is where the incoming power comes in, and then it is connected to all of the outgoing circuits that spread the load through the facilities. The incoming cable might be some huge, depending on the size of the facility, some huge 400 mil or even multiple sets of 400 mil copper cables that terminate in the facility. Then within the main switchboard, we have what's referred to as bus bar, which is a long, thick stretch of copper or aluminium, where the circuit breakers and then the outgoing cables that spread, the smaller cables that connect to all the individual appliances in your facility connect to. A main switchboard, unless they're very big loads, typically won't have loads directly connected to it. It'll connect to sub-distribution boards. When we talk about a main switchboard, we generally rate them based on their current rating. So what is the typical continuous incoming current that they can take? So it might be 800 amps or 2000 amps, which is going to be based on the bus bar capacity and how it distributes heat. If you have a small bus bar, you can't continually take 2000 amps because it'll lose a huge amount of power through the I squared R power losses. The bus bar capacity needs to exceed the value of the total connected loads by a margin, and it determines the physical side of the main switchboard. There'll also be a short circuit current rating. So if there's a fault, what's the maximum fault current the distribution board can take? With a higher rating will allow bigger fault currents. There's also going to be a voltage rating, which would be dependent on where you are. So a low voltage board will have less insulation. If you've got a high voltage, you might have a high voltage switchboard, which would have a lot more insulation. It might even be not air insulated, but insulated with special gases, which affects the clearances between components. Main switchboards also have different environmental ratings. If you're installing a main switchboard in a building, in a controlled environment where there's not a lot of dust, you might have an indoor level of protection. The level of protection is referred to as an IP rating, which is short for ingress protection. So IP20 could be used for indoor protected locations when you might have IP66, which is dust tight and you can spray water out so it's protected from rain and dust, which might be a board like this, which is installed outside. The main switchboard can also have different configuration types. You could have fixed breakers that are permanently mounted, or you could have withdrawable breakers where you could withdraw the circuit breaker while it's still in operation. This is referred to as the form of the circuit breaker. You can have a Form 1 circuit breaker. You can see the entire enclosed space. You can't access the bus bar without accessing the circuit breakers, which means to do any sort of maintenance on this board, you would need to isolate the entire thing. Or you could have a Form 2, which means the bus bar is separated from the circuit breakers, a Form 3, where the bus bars are connected, where the individual circuit breakers are separated, or you can have a Form 4, which means the entire facility, including the terminals, is all in separate compartments, and so it's safe to perform maintenance on without isolating the entire board. So main switchboard is where the incoming power terminates. If we're then distributing power through the facility, we'll likely use distribution boards. Again, your house isn't going to have, unless you have a massive house, your house isn't going to have sub-distribution boards. This will all be done in the single board where you have the incoming straight supply and maybe 8 to 10 outgoing circuits that feed your lights and direct to your appliances. On bigger facilities, you'll have a main switchboard, then cabling that connects directly to smaller distribution boards, which then connect to the separate loads. Again, only big loads, like maybe on a building, the lifts, big pumps, big HVAC units would be connected directly to the main switchboard. In other cases, you generally have sub-distribution boards which connect to all the lighting. So you might have like a 400 mil cable coming into your main distribution board. Maybe you've got like a 70 mil cable connecting to the sub-distribution board, and then to smaller circuits connected to that, you could have 4 mil, 8 mil, 16 mil cables. So distribution boards, again, they operate very similar. They're very similar to main switchboards. They're just a lot smaller, that they're used for actually connecting the final appliances, so power distribution, lighting. You could have specialist motor control centers if you're connecting to pumps, or you could have emergency boards that have separate backup UPS or power supplies connected to them. Again, same key characteristics. We've got the current rating, we've got the number of incoming and outgoing circuits, we've got the braking capacity, and we've got this bus bar arrangement in the form of the distribution board. And connected to our distribution boards are the final circuit loads. So these are things like the lighting, the socket outlets if you're plugging an appliance into a wall, motor circuits, heating, cooling, depending if it's connected directly to the distribution board or via an outlet, and any special equipment. We've also got, as we've spoken about on the fundamental sections, loads can have different characteristics. You can have a continuous load, or you can have intermittent loads that have a demand factor applied to them. Again, a toaster is a discontinuous load. You don't always have your toaster operating in your house, but you might have a security system that's always on. So they'll have different demand factors. We can have linear versus non-linear loads. Again, like linear loads are like a heater. A non-linear load has something like a rectifier or power electronics that cause disturbance to the power quality. We're also got to consider some loads might not have continuous power requirements. For example, a pump or a motor will draw a lot of power to start spinning, but once it's on, it needs less. Loads can have different power factors. You can have inductive loads that cause a lead or a lag. And it's important to understand these different load profiles to properly size the system, and it all comes back to demand factors. Everything in our facility is going to be connected by cabling. We've got cabling coming in from the street to the main switchboard. We've got cabling from the main switchboard to the distribution board, and we've got cabling from the distribution board to the final circuits. So cabling provides a low resistance path for transmitting electrical energy. It's made of copper or aluminium, which has low resistance, and it also provides, cabling also has to have protection so you can safely touch a cable without getting electrocuted. So the components of a cable will be the conductor, which is the either aluminium or copper core that transmits electricity. We've got the insulation, which will be a non-conductive layer of typically PVC plastic, which surrounds the conductor. Then you've got some cables, you might have armoring, which is steel wire armoring, which basically means that if the cable is damaged, it's got a metallic protection around it, which prevents the cores being exposed. And you can also have some sort of shielding, which is used more for communications cables to protect electromagnetic interference. Now, cablings can have a ton of different other characteristics. You can get fire-rated cables, so if there's a fire in the building, the cables don't melt and cause a fault. You can have UV-rated cables, huge thing on solar farms, so you can have your cables sitting out in the sun without the plastic degrading over time and leading to faults. And also critical to this system, we've got metering. So metering is basically the electricity authority's way of measuring how much electricity you're using so they can bill you for it. You can have revenue metering, which is on the main switchboard where you get the incoming power cable. You'll have some measure of how much current is flowing through that to calculate how much energy you're consuming so they can bill you. You can have sub-metering, which is where you put individual meters on smaller components to measure how much individual appliances are used. That's used more in building automation systems to save on electricity and smart buildings. You can also have power quality monitoring, so monitoring any harmonic distortions and power factors, transients, interruptions, which could be assessing how your facility is impacting the power quality, which again, for big loads, might be a requirement by the electricity authority. Now, throughout this entire process, we need everything to be safe, to operate, to use. To do that, we need protection. Circuit protection is if there's a fault on the system, if there's a short to ground, for example, when I was talking about earlier, when we were talking about earthing, the cable on the oven disconnects and touches the frame of the oven, we want that circuit to trip. That's what a circuit breaker does. It measures the current flowing through a circuit. There's a fault, it trips, disconnects the circuit so it's safe to operate. So it's circuit protection and earthing are fundamental to safe electrical systems. So I don't know why I've got this diagram up here, but I put it in the wrong spot. But all overcurrent protection has a time current curve. So what this means is you have the normal operating current, a multiple of that. So you can see with a normal operating current of 1, the circuit will never trip. It just operates as normal. But if you have an overcurrent of 2, you can choose different circuit breaker ratings that will determine how quickly it trips. So if you get a Z-class circuit breaker and you get a double overcurrent, so twice what the normal operating current is, it'll trip in 10 seconds. If you get a 20 times rating, it'll trip, a D-class circuit breaker will trip in 0.5 second. So all circuit breakers have this time current performance curve, and electrical designers will choose the correct will choose the correct circuit breaker so that the downstream circuit breakers trip before the upstream. What does this mean? So we look at our electrical system, which is the main circuit breaker, which is the single line diagram. If we get a fault on this motor, we want this circuit breaker to trip before this circuit breaker. If this circuit breaker trips before that one, it means when we get a fault on that motor, we lose power to our entire facility. So with discrimination and choosing the correct time current curves for our circuit breakers, we want to ensure that this breaker trips before that breaker, which is all about circuit breaker sizing and discrimination. What you're going to begin to see when we talk about circuit breaker sizings and certain circuit breakers only allow certain cable sizes is that all these components start to merge together, where the size of the main switchboard impacts what circuit breakers you choose, which impacts what cables you choose. But then you choose a bigger main switchboard, it only fits in a certain location. So suddenly all the devices it connects to are further away, which means you get more voltage drop, which means you change the cable. It becomes a bit of a balancing act. So it's really important to understand broadly how all these work and the specific design constraints and characteristics that impact them. So with cables, it's the current carrying capacity is critical, and the distance the cable has to run, which will impact the voltage drop, which impacts the size of the cable, as well as any environmental conditions like UV, like potential damage from other objects, and mechanical protection requirements. Cables can either run in conduits, which are plastic tubes that you can either install above ground or bury them below the ground, or in cable ladder or cable tray, which is open metal baskets like this the cable sits on. Fundamental to the design of any electrical system is this concept of reliability. Yes, the cost of a system, the design you choose varies significantly on the amount of connected load. That's probably the biggest factor, but after that, the next big one is the reliability you want the system to have. Does it have to be reliable 90% of the time, or does it have to be reliable 99.99999% of the time? Because that's going to inform major design and architecture decisions. If you lose power to your house, it's annoying, but it's probably not worth spending millions of dollars on a backup power system to solve a power outage every couple of months. On a data center or a hospital where uptime is absolutely critical and it's what those whole systems are designed around, then it becomes an increasingly important component of the system. You end up with secondary cables, dual redundant power supplies that support everything. And effectively, the redundancy is one of the key items that drives the overall system architecture. So when we talk about redundancy, generally what we talk about is the amount of uptime the system has to have. Again, does it have to have 90% availability, or does it have to have 99.999% availability? 90% availability means you might have like 87 hours of outages per year, when 99.99% reliability would mean you have 5 minutes of outages per year. So they're incredibly different in practice when you talk about them. So when we talk about reliability, the general way you'll see it described is whether you have an N configuration or an N+1 configuration or 2N configuration. What that means is, do you have secondary reliable components? Say you lose one transformer, do you have a second transformer that could back that up? That's an N+1 or a 2N system. So we're talking about how much reliability can impact design. If we look at a simple substation design that's a single bus configuration, it means you have one incoming circuit and two outgoing circuits. If you lose the bus bar, any of the circuit breakers, the system drops off. When you talk about a highly reliable design, you could have a double bus, double breaker configuration, which means you have two bus bars. If you lose either bus bar, the second bus bar can still operate. Each of the incoming lines has two circuit breakers. So if you lose that circuit breaker, goes down for whatever reason, you still have the secondary breaker. So you can see every component has a second reliable component, and that'll have a much higher level of reliability than the single bus system. In addition to just having secondary components everywhere, the other way we can increase the reliability of a system is with emergency and backup power. In practice, this means either having UPS battery backups or secondary generators. So if you lose the grid supply, the power drops out, the critical systems that you're powering have a secondary source of power. So there's a couple of different classifications of backup power. There's life safety systems. So this is where you're legally mandated by codes, standards, whatever, to have a battery backup. For example, in Australia, emergency lighting has to have its own dependent battery backup. So if you lose the power, the emergency lights stay on. Critical for evacuations. You could have a critical operations power. So this is where the standards for reliability are driven by business needs. For example, a data center. A data center provides internet, provides a whole lot of services. So incredibly important to the structure and design of a data center is that the users who are paying to store their servers there have a high level of reliability. Power is not going to drop out all the time. Or you could just have standby power for comfort and convenience. For example, your air conditioning, if you're in an area where the power drops out a lot, you might want a battery backup. You might want a battery backup or a generator in case the power drops out. So how do we deliver this backup temporary power? We can use generators. So you can have diesel generators or natural gas generators or a combination. Generators are made up of an engine, which is what actually provides the mechanical power, which generates electricity. They'll have a governor, which controls the speed and frequency, so it operates at the same 50 hertz or 60 hertz or whatever your grid operates at. They'll have some sort of voltage regulation to standardize the level of voltage being produced, and they'll have some sort of control system which allows either synchronization with the grid, or if they're standalone power systems, will ensure that they operate smoothly for the loads that are connected to them. So when we're talking about generators, we talk about the rating of the generator in kVA, the running kilowatts, what it produces in steady state, the step loading, so what it draws, what current it draws to start, and any future expansion if you want spare capacity. So how do we connect a generator to a power system? Well, that's where we have transfer systems. So you can have, so if you look at this wiring diagram here, you can see in normal state, the system operates, that there's normal power connected to the grid, and then there's an emergency backup generator. So when the power drops out, you flick the transfer switch, or you can get some transfer switches which are referred to automatic transfer switches that operate automatically, where you switch from the normal power to the emergency power to power your system. So again, these can be automatic that sense when the voltage drops out, they flick on the generator and switch to the emergency power, or you can have a manual transfer switch which requires a person to go and operate them. The second types of backup and emergency power supplies we can have, uninterruptible power supply. So an uninterruptible power supply is basically a set of batteries where you have your incoming power. Depending on the configuration you choose, you then have your battery bank and the outgoing power. When the incoming power drops out, the batteries begin to provide power to your system. So that's how emergency lighting systems would operate. Again, you can have really big ones that back up a whole range of systems, or you can have standalone ones that are connected to appliances. So for example, these UPS have different operating systems. You can have an offline and standby one where the normal power passes through and the batteries only activate when the power is lost. These are the most economical, but they have the lowest efficiency. You can have a line interface UPS where the voltage regulation, they provide voltage regulation without battery use, but then when the power drops out, they instantly switch on because the power is connected through the UPS. Or you can have online double conversion, which operate continuously. They're the most expensive, but they also have the fastest transfer time. When we're talking about UPS systems, we're talking about the capacity, the same as a generator in kVA. We're talking about the runtime, how long they can run, providing full load. So are they 2-hour UPS? Are they a 4-hour UPS? The efficiency, do they waste power? Input power factor, because UPS are power electronics and they involve rectifiers, they'll cause harmonics on your system because they're converting the AC to DC and then DC to AC to operate, because batteries produce electricity at DC, and the overload capacity. And then finally, there's a couple of different battery technologies. You can have valve-regulated lead acid, flooded cell, lithium ion, or flywheel storage, which is actually mechanical energy storage for short duration. Okay, next, I want to talk about the key drawings you're going to need to be able to read and understand to build, manage, interpret these systems. So the first one, and the most important drawing in any electrical system, is the single line diagram. The single line diagram describes the overall system architecture. You can look at a single line diagram, you basically see how power flows through the entire system, what are the loads, how they're connected, so on and so forth. Complex systems, You might have multiple drawings. If it's simple systems, it might just be on a single drawing. So this is how a single line diagram looks. You can see there's an incoming supply with a circuit breaker. There's some sort of main switchboard or bus bar that distributes this. You've got 3 circuit breakers connected to this. Then you have distribution boards with the final loads connected to it. So you can see in this system, there's a main switchboard and 3 distribution boards, and you can see which loads are connected to each distribution board. This is essential for showing how the system's connected, where the incoming cabling is connected, how many distribution boards you need, what circuit breakers go in those distribution boards, and where each of the loads are connected. Now, the single line diagram only explains to us the overall system architecture and the protection and all the components. What it doesn't show us is where anything goes. So that's why we need a layout diagram. Layout diagram is often plotted on the architectural layouts of building or drawing, and it shows you geographically where everything goes. So for example, this is a layout of a room. There's symbols for fans, lights, switches, so telephone outlets. From this, you can see from the layout exactly where every light's going, every facility is going. You'd have to look at the single line diagram to see which distribution boards these separate loads are connected to, but the overall layout diagram shows us geographically where everything is installed. Now, typically what you'll see on the single line diagram is you won't see every single light, you'll see a lighting circuit. The lights are then connected together in a continuous circuit, which means that if all these lights might be connected to a single circuit breaker on the distribution board, which means if that distribution board fails, all those lights will fail. It would be incredibly expensive to run separate cabling to every single light. So in a typical house, you wouldn't need that level of redundancy, so it wouldn't be required. Okay, so from the single line diagram, we understand the architecture. The layout diagram, we see all the loads, where they are, where they're positioned, where the distribution boards are, where the power outlets are. And typically on the layout diagram, we can see how the sub-circuits are connected. The final bit of information we need to build this system, and again, you might have more drawings, typicals, blah, 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 but these are just the key ones. You want a cable schedule. So what a cable schedule shows you is for each cable in this system, how long it is, what the size of the cable is, what the expected voltage drop is, how it's installed, and so on and so forth. This is a cable schedule. It shows you exactly that from the main switchboard to distribution board A, there's an 185mm cable. It's 4-core. It has these specifications. The cable schedule is going to be your key to both ordering the cables you need and then installing them. Sometimes on projects, depending on the size and complexity, they'll also provide you a cable routing diagram, which shows what conduit, what cable tray, all these cables run in. But a lot of the time, that's up to the construction team to figure out. You might also get, in terms of other drawings, again, it's all going to depend on the project and the size and the complexity. You might get individual cabinet schedules and panel schedules. So you might get an individual drawing for each of these distribution boards and the main switchboard. You might also get control panel schedules if there's control logic and control boxes going in. You might get schematic and control diagrams, and you might get additional typicals and installation details. Like there might be a typical for this type of light fitting, what it's meant to look at, or this type of light fitting that's mounted on the wall. So those are just typical drawings that you see on any electrical construction project. Okay, to wrap up, I'll just talk about some specialized components that are part of the system. We've already spoken about these a bit, but when you have non-linear loads, UPS, rectifiers, power electronics, probably going to run into issues with harmonics. So we may need to install harmonic filters or other power factor correction devices. We also have to be aware of the power factor ratio, which depends on the types of loads that are connected. So if we have a lot of inductive loads, so we have pumps or generators, we might have to have some sort of capacitor banks to correct the power factor. We can also have voltage quality issues. So that's why the cable schedule is such an essential document, because where you get voltage drop across long cable runs, we'll need to make sure we're measuring the lengths of the cables we're installing, and we're installing the same lengths as measured in the cable schedule. And if the lengths are different to the cable schedule, the cable is probably sized incorrectly. So that's a big problem on construction projects where the designers haven't properly laid out the routes or checked the lengths, or we install it differently to how they intended, and we end up with voltage drop issues because we've installed a longer cable than we had planned. Again, intrinsic to the safety of any electrical system is we'll need some sort of earthing system. So there's different types of earthing systems. and they operate differently depending on the reliability, the fault currents, and the size of different circuit breakers. So there's different types of earthing arrangements we can have on our projects. You can have, and they're referred to as TNS, TNCS, so on and so forth. So TNS is where throughout the entire installation, you have a separate neutral and a separate earth. A TNCS is where you have a link between the neutral and the earth at the load. So instead of running separate earth cable, you're eliminating the earth cable and you have a link between the neutral and the earth at the load. And in some systems, you also have an independent earth at the building or a separate earth separate from the supply earth. Again, when understanding these components, it's also essential to understand the principles of protection coordination. What this pretty much means, and I've spoken about this already, is that when you have a fault on a load, like one of these devices here, this circuit breaker should operate before this circuit breaker. It's purely done because if you get a fault on this and this breaker trips before that breaker, you lose power to the whole system instead of what should happen of just losing power to this system. The final consideration we should be aware of when we're looking at these different components is arc flash hazard. So one of the risks of electrical construction is not necessarily faults from electric shocks, but it's where you get an arc when you have a high fault current in a device and you get some sort of what's like an explosion of molten metal, which can cause people serious burns and injuries. So it's also another hazard we need to be aware of. Okay, just to quickly wrap up, I know we've covered a lot, but power distribution system, at the end of the day, is how we get the power from the generator to the load. The key principles we need to be aware of are transformation, changing voltage levels to transmit electricity over long distances, distribution, which is routing power through buildings, protection, which is how we prevent damage to devices, and safety, control, which is how we manage and operate the system, and monitoring, which is how we track and record usage and identify power quality issues. Okay, next up, we're going to talk about communication systems and try to go through it in the same sort of structure. Now, to be honest, my background is more power systems and electrical construction, like big industrial facilities and renewable energy plants. I've done indirectly through this, I've done a fair bit of fiber and communication style work, but in terms of the actual subject matter knowledge, I'm not nearly as good with communication systems. So I'm going to fly through this and I'm going to be more or less going heavily off the notes. Again, I'll put a link in the description to all the notes if you want to download them, but I'm just going to do a very brief overview of communication systems. And again, I think for construction managers, communications tends to be a much smaller part of the overall cost, and you don't really need to understand the design specifics of it as much. You're running Ethernet cables to cameras, doing fiber terminations. You've got to understand more or less the basics, but it's not what I've found in my experience. The type of projects I've worked on is that communication, you need to understand the very basics of it, but a lot of it becomes more of software configuration issues that at the end of the day, you're not really going to have any idea about. The one thing I would say is that those software configuration commissioning issues always take 100 times longer than anyone envisions. So you want to start that stuff as early as possible during the project. The same way that power systems is a transfer of power to loads, communication system is the transfer of information from one point to another through a medium using agreed upon protocols. So essential elements to a transmission or a communication system is the information source, the transmitter, whatever takes this source, maybe it's a PDF file on your computer, and it turns it into a set of data, which encodes it. Then there's a channel that it gets transmitted through. There's noise, there might be noise or interference with that channel. Then there's a receiver that decodes the message, so it takes whatever data bits of your PDF file, decodes it, and then presents it to the destination, i.e. showing it on your computer screen so you can read and interpret it. We can either have analog or digital signal. So an analog signal is a continuous waveform, sort of like AC electricity, which is how we encode voice and video. It degrades with distance and overall it's being phased out. Or we can have digital signals, which are basically combinations of zeros and one that can be regenerated perfectly. They're noise resistant and they're the standard for modern communication systems. When data is transferred, there are different data transmission modes. We can have simplex, which is one-way unidirectional communication. Think of it like a broadcast. We can have half duplex, where you have two-way communication, but it can't be done simultaneously. Think of a radio where you have to press the button to communicate. Or we can have full duplex, which is two-way simultaneous, like a phone. We can both be speaking at the same time. You can also have synchronous communication where there's a shared clock signal, or you can have asynchronous communication. Okay, so how a network's organized? Well, there's a model for this, which is referred to as the OSI model, and you can Google it. It's relatively complex, but it talks about basically how we take data from one source and send it to another, and all the different layers we attach to that data. So you want a very simplified version of how it works. You have a physical layer, which is the actual cables, connectors, and the physical signal, which is, if it's a digital signal, is just zeros and ones. These would be voltage levels. So you might have like 0 volts is the 0, 2 volts is the 1, light pulses if it's fiber or radio waves. And so this is the actual stream of bits getting transmitted. You then have the data link layer, which is the node-to-node delivery, which is where switches operate, which is where you get physical addresses. So each device on the system will have a physical address. That's where the data gets sent from and to. We then have the network layer, which is the end-to-end routing of the system. This is where routers operate, and where if you're using internet, we get IP addresses. Then you get the upper layers, which are the application services, the user interfaces that format and present our data. So the core devices in any communications network, the same as how we spoke about main switchboards or distribution boards, these are the core devices in any communications network. So we've got a switch. A switch connects devices that are part of the same network. It learns device locations based on their MAC address, which is the machine address for a specific item. They forward data only to intended recipients, and each of the ports on the switch gets used to send a certain part of data, and switches are the backbone of any modern network. So these are the local network. Switches receive a data frame, they read the destination address, they look up the address in the table, and then they forward that package of data to a specific port on another switch. When we want to connect between different networks, we use a router. What a router does is it finds the best path for data. It uses IP addresses, which is what, when you connect to your Wi-Fi, you'll get a certain IP address for your computer. That is the computer's address on that network, while, for instance, the MAC address is always specific to your machine. Routers are what make the internet possible. How a router works is it receives the data package, reads the destination IP address, consults a routing table, and forwards it to the next network. We can also get hubs, which are obsolete, that broadcast everything, firewalls that protect and filter traffic for security, and gateways that convert between different protocols. Okay, so talking in a bit more detail about addressing. So we've got a MAC address, which is the media access control address, which is the hardware address, which is physical and specific to your device, no matter what network it's connected to. They're used within the local network, so between the switches, and they have a format like this. An IP address is a logical address that changes depending on what network you're connected to. They're used between networks. Okay, let's now talk about transmission media. These are the actual cables that connect everything up. So the different types of cables we can have are twisted pair cables, which is where the copper cores of the cable are twisted to reduce interference. That's what you see when you see the blue cable that connects the internet to your laptop if you're not using Wi-Fi. These are the Ethernet cables. The most common one you'll probably see is Cat6. Some considerations when you're installing Ethernet is you can only run Ethernet about 100 or 110 meters before it loses the quality of the data transmission. You can get shielded or unshielded Ethernet, and you can also get Ethernet that has a gel protection around it, so it's safe to install underground, direct buried, or you can get non-protected Ethernet. You can also have coaxial cables, but in my experience, projects I've worked on, I've never installed a coaxial cable. It's always been Ethernet and fiber. So next up, we've got fiber. So fiber isn't copper or aluminium. It's not transmitting electrical energy in the same way an Ethernet cable is. Fiber work by transmitting light along the length of the tubes. So the advantages of fiber is you get no electrical interference. You can run fibers incredibly long distances. So running under sea floors is how they actually, from one continent to another, is all fiber, and they're secure, so they're hard to tap. You can have multimodal fiber, which you run shorter distances, such as building campuses that use an LED source, or you can have single mode fiber, which can run very long distances up to 100 kilometers that use a laser source. So we'll use fiber generally. Fiber is much more expensive. It's expensive to terminate. It's more difficult. It takes more time. But you'll use fiber generally between buildings when you have to run cables more than 100 or 200 meters. You have to install special equipment at either end of the fiber to actually terminate it and extract the cores. Then you also need to install what's referred to as a media converter, which converts the light into the electricity that is used for the Cat6 cables that connect to the end device. So you can't install fiber and connect it to a CCTV camera. You need to then break out the cores you need, then convert it to copper, and then run Cat6 to the CCTV. When you look at a fiber cable, you'll see, when you look at them, because often they're actually quite big, but the actual cores look like the hair on your head. They're tiny little cores, which is what the light transmits through, but most of the space around them is protection, tubing that prevents you bending it, because if you bend a fiber too hard, if you don't maintain the bending radius, it's very easy to crack the cores. So there's lots of protection around the cable to prevent you over flexing them and over bending them and damaging the cables. The next form of transmission media we have is wireless. So wireless is Wi-Fi, it's Bluetooth between devices, it's cellular, or it's LoRa, which is used for the Internet of Things, that sensors. When we're talking about a Wi-Fi system, we have to be aware of interfaces between other devices. Security is more complex because people can tap into it. You don't have a physical cable connection to manage, and you might have spectrum licensing. Okay, so we've spoken about the transmission media, how data moves from one section to another, the role of switches and networks. Let's now talk about the different types of networks you can have and the topologies of these networks. So you can have a local area network, which might be a single building or campus, where you have the internet connected to a router and then individual switches or devices connected to this, which is controlled by the organization. So if you're talking about a solar farm, for example, you'll have one connection to internet, a router, and then each inverter in the solar farm might have an individual switch connected to it. You can have a wide area network, which is where you have huge geographic distances, lower speeds, you have a carrier service such as something like 4G or 5G, or you can have industrial networks, which is SCADA for utilities like the solar farm, building automation systems, real-time requirements. Networks can have different structures. You can have star topology, which is where all devices are connected to a central point. This has a single point of failure. So for example, if that fails or one of these if the cable fails, you lose that device. That fails, you lose everything. You can have a mesh topology, which is where everything's interconnected, but you have much more redundancy. But again, because you've got more equipment, more cables you're running, it's complex and expensive. Or you can have a ring topology, which is what you see on most industrial networks, where you have a closed loop. So for example, if that cable fails, there's two routes to that device. It can go and route through the other way. Next, we'll talk about protocols. So protocol is a set of standardized rules and guidelines that dictate how devices communicate and exchange data over a network, acting as a common language. So IP, referred to as TCP/IP, is a standard protocol for communicating across the internet. Wi-Fi has a standard protocol for wireless networking. Ethernet has a standard communication protocol. So if we're talking about, again, going back to that OSI model, we've got physical network, the data link layer, the internet layer. So this would be using an IP protocol. There's a certain way that all these packages of data are structured. And then you've got the TCP layer, which is the transport layer, which again is a certain way that's all these packages of data are structured, which is how our internet works. When we're talking about different protocols, the key things we're talking about is whether it's an open protocol, such as the internet that everyone uses, or it's a proprietary one. Maybe there's a special one made for a building automation system. Speed capabilities, does it have distance limitations? How susceptible is it to losses in the lines? And is it widely accepted, or is it used for specific use cases only? So for example, the internet is a widely accepted protocol that everyone uses. So where do we see applications of these different systems? Now, a lot of the time we talk about internet, but internet is not the only application of network systems. We can see them in building systems where we have systems for access control, fire alarms, CCTV and security, building automation, or internet-enabled telephones. We have industrial control systems, so SCADA systems on power stations or data centers or big industrial facilities to monitor how everything's working. We use them in transportation, where we might have railway signaling, traffic management, toll systems, or you could have utility networks with smart meters, substation automation. All these different things have their own systems, their own protocols, their own structured way of doing things, but they follow these same basic communication principles. Another technology that we're seeing more and more of is power over Ethernet. So this is where you have low power cameras, PTZ cameras, access points, LED lights that are actually powered via Ethernet cables. So instead of just having a standard Ethernet cable, the cable will have two cores which will provide DC power to the device that it's connected to, and it saves you having to run a separate power cable. And again, the same as when we spoke about in our power systems, that when we have complex power systems, we need to factor in reliability, and reliability is one of the key drivers to complexity. We have the exact same issue with networking. One of the key considerations for network design is the availability level and redundancy we need. So we need 99% redundancy, which would be 3.65 days of downtime per year, or do we need 99.999%, which would be 5 minutes of downtime per year? If we need a highly reliable system, we'd need a network topology more like this. If we don't need a highly reliable system like our house, then it's fine to have some sort of star connection like this. It really depends on the specific applications, and the level of reliability will be one of the key design factors we need to consider. When we're talking about the performance of a network, we're really talking about two things: bandwidth, the speed of data transfer, and latency. What sort of delays in transmission are there? Perfectly, we want to be able to transmit gigabytes of information, download a movie in seconds at zero latency. But in practice, increasing the bandwidth or decreasing the latency is going to increase the cost of the system. The key factors that impact network performance are the cable quantity and length, the network device's capacity, the number of users, and the requirements of the applications connected to them. Okay, another important concept with network engineering is security. You don't want someone on the street to be able to access your bank details. So when you log in and send your username and password through the internet, you want to be very confident that some random person standing outside can't access it through your Wi-Fi. That's why security is absolutely essential to the design of any network. Basic principles of security is you can have physical security, such as locked rooms or secure pathways. For example, if you have a wired network, you automatically have physical security because you have to plug your laptop into that. Someone outside can't pick up the Wi-Fi signal. You have network segregation, so separate critical systems that need high levels of security. You can use access control, so logins and applications. You can have encryption, which protects data in transmission, and you can have monitoring to detect anomalies. Common vulnerabilities in a network will be unsecured devices, poorly written passwords or passwords people store on their desks on a piece of paper, unencrypted communication, so someone who can tap your Ethernet or Wi-Fi and pick up the data just simply by connecting to the network, physical access to cables or outdated firmware. Finally, what are some installation considerations when we're talking about networks? Well, the first one is that network cabling is distinct and different to power cabling. You want all your network cabling to be separated from your power cabling. This is a safety requirement. It's mandated by most codes and standards that you can't generally have in the same cable tray an Ethernet cable and a power cable. You can't have network switch in a distribution board next to live cables. We also need to be aware of things like temperature ratings, moisture protection, UV resistance if stuff's installed outstored, mechanical protection, and fire ratings. One of the biggest installation considerations I see is just how messy communications cabling is. You look at a picture like this, a lot of installations end up looking like that because often you're just running so much cabling, so many different connections, and it becomes a mess to fault find and debug. Okay, so far we've spoken about the fundamentals of electrical engineering, we've spoken about the components, power distribution systems, how you go from the load to the end appliance, and we've spoken about basics of communication systems, how we transmit information. Let's now get into more practical applications of these principles, talk about the design and construction of them, starting with the design. What is the electrical design process? How do we go from transforming client requirements into issue for construction drawings that show us exactly what we need to build? The electrical design process occurs in a couple of specific stages. We start off with the conceptual design stage, which is we look at the initial client brief and client requirements and turn these into an initial system design, looking at what the loads are going to be, where the equipment's going to fit, what sort of equipment we're going to need, and draft more or less a simple single line diagram. We then progress. Once we've got that approved from our client, once we proceed with that, we go to schematic design, which is where we start to add detail to this, work out exactly detailed loads, what everything's going to be, confirm the system architecture and size all the major equipment before we go into the detailed design development, which is where we work out exactly where everything's going to go integrate everything into the architectural designs, then finally get this approved to our client, finalize everything, and then we have our issue for construction design. So looking at the conceptual design stage in a little bit more detail. So the purpose of the conceptual design stage is to establish project requirements, constraints, and build the overall design strategy. What is the technical solution we're gonna create that meets the client requirements? We're not gonna work out the exact loads of everything, where everything's gonna go. It's gonna be very conceptual, working out technical strategy that's going to be most cost effective and fulfill our client's requirements. So key inputs to this are going to be the client brief, the architectural concept drawings and space planning, site constraints, and the power connection source and utility availabilities. Typically, client briefs will have things like an availability target, whether they want 99% redundancy or 99.99% redundancy, the level of redundancy they expect, the emergency power scope, whether we're required to provide emergency power for anything, future capacity, whether we have to leave 30% spare capacity for future upgrades, and any sustainability targets. Communications might have user counts and densities, expected network speeds, wireless coverage targets, or security system scope. Key activities at the concept design stage are going to be to assess the utilities and what power supply is available, where it's going to come, what form it's going to come, perform initial load estimations of very high level benchmarks. So for example, to building, you might do this off square meters to get an initial estimate of watts, work out roughly where the major equipment's going to be, looking at the conceptual architectural drawings, develop distribution strategy and selection. Are you going to have a main switchboard? Are you going to have two main switchboards? Are you going to have distribution boards that have separate emergency and backup supply? And are you going to have a main UPS that powers the backup supply? So developing this technical strategy and coming up with a high level architecture. The deliverables for this are going to be things like the basis of design document, a very early stage single line diagram, the equipment room locations, and a rough cost estimate. Next up, we move into the schematic design stage. So we've developed our initial technical concept, how we're going to fulfill the client requirements. And importantly, we've got that concept reviewed and approved by our client. We're going to start adding a lot more detail to this design because we roughly know what we're doing. Now we just have to start working out the exact loads, calculating everything in detail, sizing all the cables, working out where they're going to run and so forth. So purpose of the schematic design stage is really to get detailed loads, confirm the system topology, and size all of the key major equipment like the main switchboards, the UPS, the distribution boards. So we're going to take the architectural floor plans. We're going to take any mechanical equipment specifications we have. Do we know anything about the lifts? Where are the lifts going? What sort of power requirements do they have? Same with the major HVAC and any pumps. Then we're going to go through and calculate all the loads for the system. We're going to create a register of all the loads connected to the system. Primarily, we want to focus on any of the big loads and take into account their demand factors. Typically get that from standard documentation or maybe there'll be relevant standards that tell you what load factors to consider for lighting, lifts, pumps, so on and so forth. And we'll finalize our system architecture, so the distribution topology, the voltage selection, what voltages we're going to use, the equipment location, where the equipment rooms are going to be, where the communication room is going to be. Are we going to have a generator with exterior access? Key activities will be detailed load calculations, sizing the equipment rooms, the emergency power scope and definition, how it's going to connect, and we'll get our detailed single line diagrams, maybe communication diagrams, equipment room layouts, maybe very high level preliminary distribution board drawings, and again, another design package we're going to send to the client to review in detail. Once we've got all our loads, we've finalized the system architecture, we've got the exact single line diagram, well not the exact, but we've got the single line diagram we've got. Now is the time to fully flesh out our design to work out where every single exact load's going to go. We know exactly what these loads are. We're going to start routing the cables, work out where all the cables are going, because we know the load, source, the distance of the cable. We can start sizing all our cables, creating a detailed cable schedule, finalizing all our equipment, starting to consult with our vendors to confirm what specific vendors we're using, what products we're using, space proofing those products, because again, we might specify a main switchboard on an additional layout, but when we actually go talk to a vendor, they'll have slightly different layouts. Start integrating all that, basically get it to a stage where we've got, where we know where every load's going to be, how much every load's going to be, where all the cables are running, what the size of those key cables are, key vendors we should choose at this stage, where all the penetrations are going to be, and then we're also going to need to coordinate all of this with the other trades. So a huge part of the detailed design phase is because we're going to have services running everywhere. There's going to be from mechanical and plumbing, there's going to be pipes, ductwork, so on and so forth. We're going to have to start doing all our clash detection. Just going to roll into, again, final stage where we get an issue for construction set of drawings. It's free from errors. It's perfect. Doesn't miss anything. Tells us where every cable's going, where every light fitting we're installing, where the equipment rooms are, product specifications, technical specifications, and basically ready to begin construction. For electrical, it's going to give us our single line diagrams, our power and lighting plans, panel schedule, our emergency power details, and any earthing details. Communications, it's going to be the same cable routing, cable schedule, panel diagrams, equipment rack drawings, coverage plans, and then any supporting calculations such as load analysis, voltage drop, short circuit and arc flash, lighting levels, pathways, and spacings on cable trays. Once we've got the issue for construction design, what's next to do? Well, it's time to start ordering equipment, installing it, and testing it all works. This section, I'm going to talk about the construction process part I find most interesting and fun and what I've had the most experience with. I'm going to break it down into 3 core parts. Talk about procurement, so how to procure all the stuff you need, what stuff you need, how to break up packages. Talk about construction, the actual installation process, everything from putting conduits under the ground to installing cable tray, to finally laying cables, terminating them, and finally commissioning process. Okay, so let's get started with the major procurement packages. I'm going to fly through typically how you'd structure this. Again, it's going to depend a lot on the type of contractor you're working. If you're working for a general contractor who's subbing out, supply and install all the electrical systems, you obviously don't have to worry about buying all these individual components. But I want to talk about how a typical electrical contractor who's going to buy all the materials themselves before they install it would structure this. So you typically have your key electrical long lead time packages, which would be the main switchboard and switchgear, distribution boards, transformers, if there are any, and the bus duct system, if there is one. Again, depending on the project, you'll typically also have an emergency power package, which would have, you might order the generator from one supplier. Transfer switch, you might order separately, or it would probably come as part of the main switchboard. Fuel system, again, might come with a generator, might be separate, and any control panels that operate this. Ideally, you'd get this for a generator as an integrated system, for a UPS as some sort of integrated system as well. You'll then need to order all your cabling and cable containment. So typically, power cables, you'll order the larger cables from the cable schedule that have a long lead time for them from a single supplier, and you might order all the smaller circuit cables as you need them from a local wholesaler. Cable tray, no matter how good the 3D models are, it's always tough to accurately order cable tray. So typically the bends take more time to come than straight sections. So you typically order bends from the model with some allowances, and then order all of the longer straight sections and top them up as you need them so you don't end up with too much wastage. Network equipment, again, can have quite a long lead time, but that'll be all the switches and routers, the racks, any separate UPS system you have for the network equipment. Then you'd order all the lighting. So you'd need the light fixtures, emergency lighting, a lighting control system, any sensors and switches. Typically go to one lighting supplier for the whole package because you often can't mix vendors with different products. Then any of the low voltage and communication system packages such as the fire alarm system, security, the audio visual, BMS, and then finally you'll probably go to a local wholesaler, electrical wholesaler, for all the consumables and accessories. So these are the cable lugs that go on the end of the cables, terminating them, the glands, which are shown in these projects, which can actually, in my experience, glands often have a very long lead time. Any circuit breakers that are not coming fit out in the main switchboard or the distribution boards, junction boxes, labels and markers, and these would often have much shorter lead times. Now, the thing that everyone seems to miss with electrical stuff, people who don't come from an electrical background or have a lot of experience managing electrical projects, is the amount of time it takes to order this stuff. If you want a main switchboard, probably going to have to wait 20 weeks. That's 20 weeks from when you place the order, not 20 weeks from when you start negotiating with a supplier. You probably need another 6 to 8 weeks if it's an expensive piece of equipment to get quotes, assess the quotes, choose your preferred supplier, agree, sign a contract with them, get them to give you shop drawings or vendor drawings, get your designers check it, and then after that you place the order. The other stuff like transformers, I've seen lead times of 70 weeks by the time it comes to site. So you're ordering electrical equipment, you need to have a procurement schedule and you need to understand how long this stuff takes. In an ideal world, we'd get an issue for construction design and then we'd have 30 or 40 weeks to place the order for this equipment. No project on earth works like that. Never have enough time to do this. So in practice, you place all your orders for the long lead time electrical equipment at the 60% design stage, and you just need to approve the shop drawings quickly, keep the ball moving, manage the contract, and make sure that you're coordinating all the factory acceptance testing just to move the process along as fast as possible, because no project I've ever worked on has ended up tons of time to order this equipment. It just takes so long to come. So key issue with electrical procurement is managing lead times. Now, vendors will typically need to provide you, depending on the complexity of the equipment, they'll need to provide you shop drawings, data sheets that you need your designers to approve, samples for light fittings, but there's some sort of architectural element, coordination drawings, calculations, and equipment schedules. We would want all this documentation reviewed before we place any orders. Typically, we want our designers to review it and then to basically make sure everything's going to work, because the vendor specifications on the product, unless it's purely custom made for your project, are always going to be slightly different to the design. So it's essential for ordering anything, the design team checks it off and approves the shop drawings. On top of this, depending on the equipment we're ordering, is we probably will get some factory acceptance testing done. Again, we'd get some insulation testing or operation done in the lab for switch gears, transformer insulation testing, generators, we may get a load bank test, or cables before they get shipped, we might do an insulation resistance testing. On top of this, we need certification, so type testing certification has been approved, test reports, material origin certifications, and warranty documentation. Again, this whole thing, I just want to highlight is the amount of time it takes stuff to arrive on site. If you look at something like a switchboard, you say you start at month 1, you allow 4 weeks for the vendor selection, 3 weeks for the contract negotiation, 4 weeks for the shop drawings, 20 weeks for the actual fabrication, a couple of weeks for the factory testing, and then a couple of weeks for it to get shipped and delivered. You're easily looking at 9 months from when you start the process to when the equipment is on site. So it's essential when managing electrical procurement that you're thinking, it's always at the front of your mind, how long this stuff takes to order. Once we've got all the gear on site, what's next? Well, it's time to start putting it all together, and that's where we enter the construction phase. So I've broken the construction phase up into a couple of separate steps. Enabling work, so all the in-ground services and preparation, the actual infrastructure, so putting in the cable tray, installing switchboards, the cable installation, so the cable pulling and the cable terminations, and the finally installation, termination, and the final configurations of all the equipment. So starting with the initial construction. So the first stage of any electrical project is the underground installation. So this is where you run your pits and pipes underground, you drill the foundations for your light poles, you run conduits through the slab. This is heavily coordinated with the civil and structural works, and it's essential that electrical people are managing this, because in my experience, when you have civil people doing this work, always end up with missed conduits, blocked conduits, things not connected properly, conduits missing from the drawings. It's really, to me, this isn't a civil construction activity. Installing these conduits, penetrations, earth grids, it's electrical construction. It needs to be managed by electrical people. The next stage happens after you've had the initial civil works, the slabs, the structures. It's when the building structure's up and we start to put in all the infrastructure needed for construction. So this is where we put in our cable tray and cable containment. We mount any surface mounted conduits. We install any pits or pull boxes. We put in supports, structures for lighting, these sorts of things. Typically, we'd put in our main distribution routes first. So these would be the larger cable trays. This stage, we'd put in any sort of smaller branch containment and the final drops of devices at the same time as we install the devices. And we'd fit out our equipment rooms. Assuming we have the equipment at this stage in the project, we'd put in all our switchboards, our main switchboards, our distribution boards, any transformers, or all the big equipment within the rooms. Once all the cable trays in, we've installed the devices, we can start our cable pulling. This is when we basically run out all of the main cables. Typically, we'll install the main feeder cables first, bigger cables, the sub feeders, and then any branch circuits we may do separately or we may do it at the same time as we install the devices. Again, to do this, we use cable pulling, so things like cable drums. We'll install the cables on drums, cable pulling lubricant. If it's direct buried, we would have had to do this as part of the civil works, or if it's done through conduits, we may use a winch as well, or some sort of mechanical aid, depending on how big the cables are, how tough they are to install. And it's essential during this stage, again, that we're separating power and communications cable and we're identifying our cables. We're writing the name on them, the location, where they run to, so we're not wasting time retesting everything and trying to work out where all the cables have been run. Now, once all the mains cabling in, the cable trays in, the next step is to go through and install all our devices. So for lighting, we're mounting fixtures, the emergency light fittings and the brackets. We might be installing power outlets. We're mounting our disconnector switches, so on and so forth. And again, this is heavily connected with building fit out. So putting up the walls, coordinating all these tasks with the building construction. So the fit out is heavily coordinating with building fit out. And then once the devices are in, we run all our cables, we need to go and terminate all our cables. So this is where we just, from the cable, once we've installed the cable, we just have an end of a cable. We need to cut the ends off, install the lugs, crimp the lugs, put on the heat shrink and terminate all the earthing. Then we've got our fully connected electrical system. We're talking about how this happens in time. Again, we start with civil works and the interface with the civil construction. Once the structure's up, we put up all our cable tray and our main cable tray, and we can fit out our equipment rooms, assuming the procurement's been done on time and we've got our main switchboards and keyboards. Then once the cable tray's up, the structure's up, we can start running all the cables within the cable tray. Then in parallel with building framing, building construction, building fit out, we can install all our devices and begin terminating our cables to fully complete our electrical system. Now, so far, we've installed everything exactly as per the design drawings, but it always happens on every project, that there's issues with what we've installed and there's issues with the design. So basically, final stage in this process, procurement, construction, now commissioning, we want to check that everything's working correctly. I love this diagram because this perfectly explains the role of commissioning and the different types of commissioning. So what happens in the process of a construction project is we end up with our initial requirements. The client wants 99% reliability, they want lighting, they want power, they want emergency power. We move through the design stage, which we already spoke about. We add more and more detail. The system design, the subsystem design, the module design. Finally, we get to an IFC design with detailed circuit drawings. The role of procurement in construction is to build exactly what says on the drawings as detailed in the drawings. Now, what happens when we've built is we go through a series of quality assurance and commissioning. Construction quality, the role of it is to check that what we built matches the drawings and specifications. Commissioning is then all of these stages of the process where we're validating that the design, the way it's been installed, fulfills the requirements. So the end stage of commissioning isn't testing that cable A goes to cable B. It's testing that the room meets the lighting requirements. We're testing the initial requirements to assume they've been fulfilled. So commissioning starts in the pre-commissioning phase, or also referred to as the construction quality assurance. This is where we test that everything has been installed correctly as per the design. So we do insulation resistance testing on cables, where we measure the core of the cable and the resistance of that to earth. We should get a very high rating, which means the cable has not been damaged anywhere. There's no nick on the insulation. There's no pathway to ground. So we're checking that the cable is safely insulated. We do continuity testing to test the cables have been run from point A to point B correctly, as per the drawings. We do polarity checks to check the red, green, and blue has been installed correctly. And we do visual checks that there's torque marks, labeling's installed, there's clearance, there's no damage. And we document this with the construction as-built drawings and test certificates. Once the construction quality assurance and pre-commissioning is done, we're 100% confident that what we've built matches the IFC design, which is when we can go into the commissioning test. So commissioning is all about checking that what we've installed, what the design has designed is meeting the original requirements. So we do things like second parent system injection tests to check things are working correctly. We look at protection relay settings, make sure everything's operating. We test that, for example, if we have an emergency backup power supply, that the automatic transfer switch operates. We might do load bank testing on our generator, measure power quality. Basically, we want to verify that circuit breakers are coordinating, that there's ground fault protection, arc flash settings, transfer timing, all these things are configured correctly. We'll do the same thing for our communication system. And then the final stage of testing is our overall system configuration and integration, which is checking that the whole system is operating correctly, that we're validating things like the initial requirements said that we needed to have 70 lux in this room, that we're testing with a light meter that we do in fact get 70 lux. So we're testing the initial specifications, the initial requirements. And then the final stage of this process is we're bundling everything up and we're handing it over to our clients. We've done all the quality assurance, we've done all the commissioning. They may even witness some of the commissioning, so they're confident. We're going to finally submit all the documentation we've produced on the project. The as-built drawings with all our red line markups, network diagrams and IP schedules, configuration backups, test certificates, operations and maintenance manuals, emergency procedures, and a password register. We might also have to undergo training for them, op training on how the power system operates, how to safely do isolations, the alarm responses. They'll give us a list of defects to close out. Any defects I've identified, we can close that out. We can give them the spare parts in our warranty register, and we can finalize the overall project. You can't complete any discussion of electrical engineering or electricity context of construction without talking about safety. So next, we're going to go through principles of electrical safety, which are absolutely essential for any construction manager to properly understand. So basically, this section is all going to be about how to ensure that no one gets hurt when both dealing and working on electricity and electrical systems, but also working around them. So first off, understand the risks. What are we trying to avoid? There's really two things we're trying to avoid when we're dealing with electricity. One is direct electric shock. The other, arc flash hazards. Biggest one, the one we'll spend the most time talking about, is electric shock, but arc flash, particularly when you're dealing with large industrial systems where there's a lot of power, a lot of current flowing through, arc flash is also a serious hazard. So, electric shock. Electric shock occurs when the human body becomes in contact with a live electrical circuit. The current flows through the body where there's contact from the person to an energized conductor, and then they form a path between the live electricity and ground. This can happen couple of different ways, and effectively what happens is the current passes through your body, can pass through your heart, giving you burns or even worse, stopping your heart. So the first scenario that this can happen under is where what we call a phase to ground shock. It's where simply, as you can see in the diagram, a person is coming in contact with live 240 volt HP, whatever it is, electricity, and they're forming a part between the live wire and the ground with current flowing through the body. The second type of shock is a phase-to-phase shock, where someone comes in contact with two separate live wires that are at different voltages. And again, because there's a potential difference, the current will pass through the body. So what impacts the degree to which somebody gets a shock? Well, the first one is the level of voltage. The higher the voltage, the more current that's going to flow through your body, the greater the degree of the shock you're going to get. So if you touch 11 kV, any HP voltage, you're almost certainly going to die. If you touch DC 10 volts, what is in your laptop or your phone, could get a tiny shock, but really it's not going to be significant. The other factor that impacts the severity of the shock is the resistance of your body. If you have dry skin, you'll have higher resistance, which means the current is harder to flow through you. If you have wet skin, you'll have low resistance. That's why when you see people working on live wires, they're often wearing rubber boots, which is increasing the resistance of their body through the ground. Also, where the shock actually affects you. So if the current path is across the chest, if power is flowing through your actual physical body, the shock's going to be much worse than if when, say, an electrical wire touches your leg and goes through to the floor, the shock's going to be different. It's not going to be nearly as severe. The other factor that impacts the severity is the duration of the shock. Obviously, the longer you're in contact with electricity, the more dangerous it is, and the frequency. So around 50 to 60 hertz is actually most dangerous to the heart. Now, the level of current that flows through your body is going to be proportional largely to the voltage that you touch. If you touch, as I said, 11 kV, you're going to get a much worse shock than if you touch 12 volts DC. But in terms of the actual impact on the body of this current, if we're talking about 1 milliamp current, it'll be barely perceptible. But if we're talking about anything above 100 milliamps, we're talking about burns and tissue damage. The other way that people can get hurt with electricity is through arc flash. So arc flash is when you have an explosive release of energy when current flows through an air between conductors to the ground when it occurs. That's what lightning is. That's where you see that bright light, the explosion. That is current flowing through the air through an air gap, which causes the air to ionize, which becomes conductive plasma. Current flows through it and huge amounts of heat, light, pressure, and sound are released. That's why you hear the massive explosion when there's lightning. The same thing happens in circuit boards where there's a fault and there's an arc between a live conductor and the grounded frame. Where do we often see arc flash triggers during electrical installations? What happens when people drop tools across bus bars, when there's incorrect voltage testing, when they're racking breakers in and out. So often when you actually disconnect live circuit breakers, there's an intentional arc that develops. You can get it when there's the buildup of dust and contamination, which bridges the gap between a live and ground conductor. Failures during insulation, maybe rodents or pests bridge the gap and cause an arc flash. Or generally, the risk occurs whenever there's work around or on energized equipment. So when an arc forms, what happens? Well, first, huge temperatures develop in the arc center, around 20,000 degrees Celsius. There's a huge expansion of air, which causes an explosive force, which is why you hear the very loud clap of thunder when there's a lightning strike. You get very intense light, strong UV, which can cause instant burns. And you also get some molten metal when the conductors actually expand and can vaporize. That's when you see failed electrical circuit, there's always burning or there's always some sort of molten metal. The severity of an arc flash event is completely dependent on the available fault current. That's why you won't get huge arc flash events in your house, because there's just not enough power going to your house. But in an industrial facility where you have a 4,000 amp switchboard, you can get huge arc faults even on low voltage equipment. The arc duration, so the longer it takes to clear the fault, the longer it takes the circuit breaker to operate, will make the arc fault worse. The working distance, so how close you are to the actual explosion, the closer you are, much worse. Further away, it's obviously better. The gap between the conductors, and also whether the arc occurs in an enclosed environment. So most modern switchboards will actually have specialist arc flash venting. So when there's a fault, it contains the arc and ventilates it out the back of the switchboard where it's likely that someone isn't going to come into contact with it. Okay, so next up, I want to talk in a little bit more detail about earthing, how earthing protects you from electric shocks, but also how earthing alone might not, and particularly with high voltage installations and power plants, earthing alone isn't sufficient to protect people from electric shocks. So what happens when you get an earth fault is that you have a piece of equipment, a switchboard, could be an oven in your house, a toaster, whatever it is, the live wire comes in contact with the frame. Now, in a properly designed system, when the frame is connected or bonded to earth, so when the fault occurs, current flows through the frame into the earth conductor, which should have sufficient current that causes the circuit breaker to trip. If the equipment isn't earthed, when the live wire touches the frame, there will be no fault current because it won't be able to flow to ground. And it'll sit there at 240 volts, whatever it is, until somebody comes along, touches the frame. That is when they bridge the frame to ground, and that's when the fault occurs, and it's why you get a shock. So in normal conditions, the current flows from the source through the conductor to the load and back through the neutral or return path. In a ground fault condition, the source flows through an unintended path to earth, back to the source, or if there's no earth, you become that unintended path and you come up and you touch the piece of equipment. Now, touch potential refers to the potential the equipment frame could be at, assuming it's not earth. If it is earth, the resistance from the frame to the return path, so that earth bond might have some resistance in it, could have a touch potential. So you could have a situation where if there's sufficient voltage or the earth is far away enough from the earth at the transformer to complete the circuit, where there's actually resistance in the earth part. So even with, and if the equipment's probably not earth, if it got a huge fault current and you have a tiny 6mm earth, you'll run into the situation where even if the equipment is earth, because there's resistance in the earth part, the frame could still have some sort of touch potential. That's referred to as earth potential rise. Other reason you could have a grounded system, so that's referred to touch potential, where you have resistance between the frame of a faulted structure and the actual earth. Other way, you could even have a properly grounded system and you could still have some sort of, people could get some sort of electric shock under a fault condition, refers to step potential. So what happens with step potential is, if you can imagine with this faulted structure, the return path of this live conductor is back at a transformer kilometers away. That the return path is when there's a fault. It should flow through the structure, flow through the earth, back to the earth at the transformer, completing the circuit from the fault. What can happen is if you have a poorly designed earth grid, when you're actually, this person stepping here is creating a potential difference across their legs, because this point, the fault, say this live wire is at 11,000 volts, 66,000 volts. That point there might be at 200 volts or whatever, or that point there could be at 66 volts or whatever it ends up being, depending on the design of the earthing system. That this earth actually, because there's resistance between this point and the origin of this supply to complete the circuit, that you can actually get a slowly degrading earth ring where you might get 66,000 volts here, 55,000, whatever, however it degrades, that when someone actually steps and causes a distance across their legs, you can actually get this. This occurs in power stations. This won't occur in your house. That a potential difference arises across their legs and they can actually get an electric shock from that. So that's why, particularly in power stations, high power facilities, and I actually don't understand this stuff that well. Earthing is more or less black art, super complex how people work all this stuff out, but you can actually get potential differences. Someone can get electric shock just from walking away from a fault. So that's why earthing on big complicated structures, big complicated high power systems, power stations, becomes so incredibly complicated, and it's more or less an independent discipline from other electrical engineering. Okay, so that's more or less how people get shocks or how arc flash faults occur. Let's now talk about fundamental principles of electrical safety. So first thing I want to talk about is the hierarchy of isolation, basically talking more or less at high-level principles, not in specific tactics, of how we deal with electrical safety. First way we do this is referred to as the hierarchy of isolation, is we want to design out the hazard. So for example, we want to actually eliminate the need for electrical work in the first place. Can we avoid doing any sort of live work? Can we energize the whole facility at the end of the project when no one's going to be working around live conductors? So that's designing out. The second principle is actually de-energizing before we do the work. So obviously we don't want to work around or near live power sources, so we remove the electricity. Next is physical separation. So if we have any live parts or components, there's a physical separation between anyone working and the hazard. If we can't maintain physical separation, we need to put in place barriers to prevent access to the energized parts. And the last resort is to actually put in place PPE or protection when doing it. This is when people have to work on live electricity lines, or when they're working around high fault currents, they'll actually wear arc flash protection suits. So that's the last resort, is personal protective equipment. Now, while it's all well and good to say to de-energize and design out and to avoid working on any live electricity, on complicated projects where there's circuits running everywhere, there is always this challenge of being 100% sure that what you're working on is not live. So this is referred to as the zero energy principle, where all sources, primary, backup, stored energy, and this doesn't just apply to electricity, this can apply to mechanical systems as well. If you're talking about working around pumps or generators, putting in place processes so that you can't actually energize the generator when people are working on it. You want physical disconnection, not just the switch being off, but a physical gap between the energy source, the voltage source, and where people are working. Visible isolation points, and we'll talk about this more when we're talking about the lockout tagout procedure that people use on construction projects. Everything is locked in an off position. People working on actually put a personal padlock on the work, and they have the key to it. They're the only ones that can remove it. That any stored energy in a system is dissipated. So for example, if you have a capacitor bank or something like that, that it's actually earthed and the electricity from it is dissipated, because you can get on large circuits, particularly really, really long cables, that even if the power is disconnected, a long cable between a cable core and the screen can act as a capacitor and actually store charge. So when someone comes along, touches it, they'll get a shock. And that everything on top of all these controls, before anyone does any work on anything, they actually test it to make sure that there's 0 volts. Basically, what this all means is that switching the power off just isn't enough. Switches can fail. They can fail in the closed position. Control circuits may be auto restarted. You can get backfeed from other sources if you haven't properly gone through the drawings and isolated everything. You can get induced voltage from parallel circuits and stored energy in systems. Overall, switching the power off isn't enough. You need a comprehensive way of doing a complete isolation procedure. So at the end of the day, before anyone works on any system, they have to test that it's properly isolated, which comes down to the 3-point test protocol. 3-point test protocol is testing the meter on a known live source. What this does is it proves that the meter you're using actually works and registers a voltage. Then you test the target circuit to prove it's dead, and then you test the meter again to make sure it's working correctly. This system basically ensures you're not using a faulty meter or nothing's gone wrong in the testing, and it has been properly tested and proven that it's dead. Now, behind this all is the lockout tagout procedure. The principle behind this is that the person doing the work is responsible for putting in place the isolations that they're working on. And this is all done through personal isolation locks. And the person doing the work looks at the drawings with an isolation officer or someone who's a permit officer, someone who's in charge of doing the work. They agree to all the isolations. They look at all the isolation ports. They look at the drawings. They confirm, yes, it's isolated here. Yes, it's isolated here. Yes, it's isolated here. I'm happy. Then they go through and they put a personal padlock on every single isolation point, and they have the key to that lock. Why is that critical? Because say there's some confusion, some miscommunication. Someone thinks the circuit is safe to energize again. They don't realize that this person is still working and in contact with the circuit. Someone could just go and flick the circuit on. With it actually being physically locked off with the person working on the circuit having a key, it's impossible to happen. Someone can't go and simply switch it on because it's locked in the off position with a personal padlock. The person doing the work has the key to that padlock. Electrical safety starts in the design phase. It's not just the construction problem. It starts all the way back when we're looking at the requirements of the project and trying to understand them. And that is why electrical designers are inherently part of the safety process. Simplest way this is implemented is with isolation points in the design. Every component of an electrical system should have visible disconnects at each equipment, should be lockable in the open position. So you should be able to place a padlock to isolate the circuit. The load breaks should be sized for correct, safe operation. So if you're sizing a circuit breaker, it should be able to interrupt current at the safe operating voltage. It should be accessible. Operating those switches should be accessible without exposing someone to hazards. And then everything needs to be labeled crystal clear, and the labeling needs to match exactly what's on the drawings. Second part of electrical safety and design is the earthing and bonding design. And that is basically having an earthing system where there's always a low impedance path designed for the fault currents of the system, and it enables protective devices to operate. So there needs to be sufficient current flowing through a fault that, it triggers the upstream circuit breaker. If you don't have a sufficient fault current, if you have a low fault current, you can have an equipment that's in fault. The circuit breaker doesn't trip, so the system still remains in fault, the hazard that someone can touch it. You also need to maintain all touch potential. So when we go back to touch potential, we're talking about this situation should always be at less than 50 volts. So when there's a fault, someone could walk up and touch the faulted equipment and not get a dangerous electric shock. All exposed metallic equipment that has power running to it needs to be bonded to earth, and this eliminates voltage differences between equipment and between different metallic surfaces. We spoke about the different earthing types, but the correct earthing type has to be chosen for the project, dependent on the fault currents, the system design, the layout. Critical design elements when we're talking about an earthing system will be the earth electrode resistance, which should always be less than 10 ohms, the bonding conductor size for the specific fault currents, the earth fault loop impedance and how that impacts circuit breaker sizing, and coordinating that with the protective device settings. In addition to isolation points and earthing, another critical principle of electrical design is segregation and separation. Different voltage levels, power, comms, everything should be separate, clearly labeled, and everything should be easily isolated. So you could isolate high voltage without impacting low voltage, which means things need to run in separate cable trays through separate conduits. You need physical separation between high voltage equipment, low voltage equipment in separate rooms. Basically, you're trying to set up a situation where people can safely work on a system and not have to interact with that other system whatsoever. All the equipment should default to safe operation, that if something's wrong, it doesn't, for example, a circuit breaker has a failure, it shouldn't fail to being closed, it should fail to being open. So everything should default to safe, and you should have maintenance. The operations and maintenance of the system should be considered. For example, if you have to do checks for whether a circuit's in fault, that there's infrared scanning windows rather than someone having to open the panel. You have test points accessible without exposure, that you can remotely rack and close circuit breakers. Everything's labeled, everything's really easy and safe to use. And finally, all our protective devices coordinated and selected to clear faults at the lowest possible level, that upstream devices can remain closed, that the downstream devices trip first. We're minimizing the outage areas, that all the circuit breakers are also sized in accordance with the arc flash requirements. Remember we spoke about with arc flash that the longer you have a fault, the worse the arc flash is. So you want to clear your faults fast enough that the arc flash level's safe to walk around to operate in. So if you have a worker standing in front of a main switchboard, there's a fault, that you don't get some huge arc flash that puts them at risk. So that's the design side. What about tactically? How do we talk about electrical safety in construction? First one is pre-task planning. Again, this applies to any construction activity, whether it's civil work, mechanical work, whatever. Risk assessments for every task, asking yourself what could go wrong, what energy sources exist, can it be eliminated, is live works absolutely necessary, what controls are needed, lotto, barriers, PPE, and is, particularly for electrical work, is the person doing the work qualified to be doing it? Now, I mentioned this before, that lockout tagout is the principal way when you have energy introduced into a system, how the people working on that system manage their own safety through a lockout tagout procedure, where it starts with pre-task planning, identifying what is the work, what are the systems they're going to be working on, what systems are they going to be working adjacent to, how do we isolate those? Typically on a project, you'll have an authorized isolation officer who's responsible for coordinating all of this. They work out where are they working, what are they going to be working near, they look at the drawings, they review the drawings, they plan the isolation, they determine what systems are effective, where are the isolation points going to be. In coordination with the people doing the physical works, they go through, they isolate all of the equipment together, they put padlocks on it, they shut it down, they take the keys that they're working on, either the individual has the key to their own lock, or they lock the keys in a separate container where everyone has personal lock. The only people who can open that container are the people doing the work on the system. They go through, they verify all the isolations are correct, test meter, then and only then they can issue an isolation permit and it's safe to work on. When it's absolutely unavoidable, and in certain situations it is, there will be situations where people need to work near or on energized equipment. in which case they'll need insulated tools and barriers. They'll always need to work in groups of 2, so you have a worker and a safety watch. They'll need to understand electrical rescue procedures. They'll need arc flash rated PPE dependent on the expected level of fault current. So you can see a situation here when someone's dressed in arc flash rated PPE, and they'll also need to minimize their exposure time. Final thing I want to talk about is temporary power management. Now, it's often quite a challenge on construction projects because you need temporary lighting, people need power equipment and tools. There often ends up being quite a significant amount of temporary electrical works. Principle behind these is that you have RCD devices fitted on everything, and that systems are properly designed and installed by competent professionals, i.e. electricians. An RCD, the way it operates is that you have a normal electrical system with an active and a neutral. An RCD is a very sensitive device that measures if any current if there's any difference between the active and the neutral, so there's current leaking somewhere. If that's the case, it will trip the circuit and stop operation. In this video, I'm going to talk through some key challenges every single electrical construction project runs into. Doesn't matter whether you're working on commercial projects, infrastructure, renewable energy, oil and gas, whatever. I can guarantee these challenges will come up across your project. So I'm going to talk about what these challenges are and give you some simple strategies that you can do to try and mitigate the impact of them. Number one, differences between the IFC design drawings and the vendor shop drawings. When the designers produce the initial electrical design, typically going off standard dimensions, standard current ratings, standard equipment. They haven't chosen specific vendors for you to use. You, as the construction team, go into your procurement, choose vendors. The vendors you choose always have slight inconsistencies between what the original designers spec'd. Every project I've worked on, this has caused headaches with minor dimensions being different, minor power ratings being different. It's just an incredible, painful process. I don't know if there's a good solution for it. But the only thing I can recommend that you do is get shop drawings. Number one, choose your vendors as early as possible. Get shop drawings for them that detail all the relevant information, dimensions, widths, power ratings, whatever. And that you get the designers to check these and to check these properly, because they will almost certainly be different from what they've originally spec'd. Number two, and this is directly addressed at all my civil and structural friends who haven't worked on electrical projects before, that the amount of time you need to order, buy electrical equipment is absurd. Switchgear and transformers can take 20, 30. I've ordered transformers that have a 70-week lead time. That's from when you actually place the order to when it arrives on site. That doesn't factor in all the time negotiating the contract, getting quotes, choosing the correct vendor, getting the shop drawings approved by the designers. All this stuff takes an absurd amount of time. Even specialist, high voltage, fire rated cables can take 12 or 14 weeks to come. And at the end of the day, if you need stuff faster, you end up having to pay money you don't have. Again, the only solution to this problem, and it's not pretty, is that you need to order off a preliminary design. No project will give you enough time from IFC to when you make the order to order the equipment. Number three is the civil interface challenge. Most civil engineers, supervisors, and work crews just fundamentally don't understand how to read electrical drawings or the implications of minor changes and variants. Every project has challenges when civil, foundation, and structural works are occurring, and when the initial electrical enabling works, like installing the underground conduits, the earth grids, and so on, always causes these interface problems, and you end up with all these tiny quality assurance issues, design changes that cascade through delivery. On top of this, for whatever reason, the civil drawings never seem to line up with the electrical drawings. You miss installing conduits through slabs that require expensive core drilling later. The wrong type and size of conduits get installed that either need to be changed or rework done later. You get conduits that are crushed by reinforcement or filled with concrete during pours. And earthing electrodes seem to quite regularly get completely forgotten. Now, the only solution I see to this problem is that you need an electrical team early, an electrical supervisor who's the one coordinating and doing this installation. Every time it's not the electrical team doing it, end up with these exact problems. Number four, And I think everyone who works in services is aware of this problem, is that services always clash. No matter how much BIM modeling is done, how many coordination meetings, services always clash underground or in ceiling spaces. And because electrical is always last, and everyone seems to think electrical is the service that can easily be relocated, electrical is the one that ends up with the most changes. And unfortunately, I don't really see a good solution to this problem. I guess over time, as BIM modeling and AI tools get better and better, it'll slowly become less and less of a problem. But there just always seems to be this issue with translating 2D drawings into practice, into reality, and installing them. It's just an incredibly challenging task. Number 5, which again happens on lots and lots of projects where there's any sort of staged handover or completion, or there's any sort of significant commissioning program, that projects always energize parts of the electrical system before construction is fully complete, which introduces live electricity, which introduces significant safety risks, also introduces this huge administrative burden of a lockout tagout process and performing safe electrical isolations. In theory, project managers always have this idea that you can start commissioning before the construction is fully complete. And yes, it does work to a certain degree, but what happens when you start turning the power on, you cause all these other cascading impacts, all these challenges of working on a partially energized system, which causes all these issues with permits to work, hazards, delays, and temporary feeds can significantly impact the actual construction works, not to mention the dangers it exposes the workers to. What I tend to see happen is that the strict procedures introduced through partial energization, and if you do partially energize stuff, you do need strict procedures to manage it because it's incredibly dangerous. That almost causes more disruption than just waiting for the construction to finish and then starting the energization. Number 6, which again is a hard one to ever do something about, but it's where you have minor specification errors or misinterpretations through procurement, through construction, that cause major consequences during procurement. And I see this happen all the time with communications equipment. Construction teams don't understand the consequences of minor changes or might miss little specifications. And what happens, they make these incorrect assumptions that cause big problems during commissioning. The types of problems I've seen: incorrect IP ratings of equipment, incorrect UV protection of cables, having to go through a whole solar farm and install additional mechanical protection because the cables we ordered weren't UV rated, inconsistencies with phase rotations, metric versus imperial sizing, missing certifications that the inspector won't approve. All these minor errors aren't picked up until the late stage of the installation and moving into commissioning. The biggest strategy I see to overcome this problem, again, I spoke about it during procurement, is getting the designers to review the shop drawings so everyone knows exactly what you're ordering. They check it against the specifications, they make sure it's correct, and then again, to get the commission, maybe not, again, in contrast to what I just said, to try and get commissioning started, supporting construction, reviewing the construction quality assurance as early as possible, even if it doesn't mean energizing things and introducing the safety risk. Number 7, a hidden cost blowout. Electrical projects always have these hidden costs that are difficult to budget for, estimate, but are essential to doing the work. Things that always cost more than people think: temporary power requirements and any sort of work around live systems, partial energization, or working around existing utilities always costs more than people think. Surprise costs that aren't that surprised because they have it on every project could be temporary power that's needed for 12 months, not 3 months, premium time for any shutdown work or night works on any sort of isolations, paying additional acceleration fees when equipment's ordered late, core drilling for missing conduits, rework associated with failed inspections, extended commissioning to fix problems, and redesign when site conditions don't exactly match the drawings. These surprises always add 20 to 30% to electrical project costs. Okay, so what's the low-hanging fruit you can do on your project to try and solve these problems? Well, number 1 is to start procurement early. In practice, you're not going to be able to order off an IFC design, so you should start it as early as the 30% design, or even start engaging with suppliers to understand who your preferred ones are, getting budget pricing, going through the whole process so you can get your equipment ordered as soon as possible. Because that is going to be the key thing to the schedule of any electrical project. The next one is having the electrical team manage the civil electrical works, any penetration through concrete slabs, that everything's checked off. You get someone who knows and understands electrical drawings and the implications of changes to be managing these. That as soon as you get vendor drawings, that they sent to the design team to check them against the specs to make sure that there's no mismatches. The final one is to start commissioning as early as possible without introducing power, and to build a realistic and accurate commissioning schedule and then add 50% to it. Every project you work on, you're going to deal with long lead times, different teams managing electrical work, coordination between trades, service clashes, all these problems. Again, it's just about understanding what's likely to happen and being as proactive as possible when dealing with it.